So a very good afternoon to all of you. I am here to clear any doubts that you may have in the course transport phenomena. It could be on any specific question or on any specific topics. And assisting me today is the senior TA for the course, Ms. Manikuntala Mukhopadhyay, who's also present. And together we will try to address any queries or doubts that you may have regarding this course. Good afternoon to all of you. I am here to clear any doubts that you may have in the course transport phenomena. It could be on any specific. So I would request the NPTEL specialists at IIT Kharagpur and also my TA to let me know if there are any specific questions which I can address immediately, or as the time progresses, if there are any questions which come up, I would try to explain the doubts or specific queries as well.
Sure, sir.
So I would request the NPTEL. So Manikuntala, there's some echo coming from your side.
Yes, sir. I have muted my YouTube live session right now. I don't think there will be echo anymore.
Okay. So is there a specific question?
Yes, sir. Okay, so Mahadev has asked that he is having some problem regarding the concepts on boundary layer, and he wants to know that how will the hydrostatic, or what will be the hydrostatic boundary layer on a curved surface and flow between two parallel plates, if one is moving and the other is at rest, and also how will the pressure variation happen on such surfaces?
So there are three questions, I think. One is about the concept of hydrodynamic boundary layer. The second is flow between two parallel plates. And the third one I did not get clearly. It's about the pressure variation for which type of flow? Flow between parallel plates?
Yes, sir, on such surfaces, if one is moving and the other is at rest.
Okay. All right. So that's one question. And I can probably show the relevant slide, which I have shown before, and once again explain the concept of boundary layers. So let me just find the right one, and then I'll share my screen. Okay. Manikuntala, is it visible? The slide on external incompressible viscous flow?
No, sir, the slide is not visible yet.
Yes, sir, visible from our end.
From your end, it's visible?
Yeah.
Okay. So I would go ahead with the explanation, and probably it will come to Manikuntala after a few minutes. So since it's visible at your end, I hope that it's going to be visible to the student, to all the students who are. Okay. So what we have for the case of a hydrodynamic boundary layer is that, let's say there's a flat plate and a fluid stream is approaching it with a constant velocity, which we call as the approach velocity and denoted by the symbol capital V over here. Now, since there's a viscous interaction between the layers of the fluid, which are moving past one another with different velocities, when they encounter the solid plate and start interacting, due to no slip condition, the layer which is just above the plate, adjacent to the plate, they will have zero velocity, and the velocity will progressively increase till it reaches the free stream velocity, which is known as the U infinity. So inside this layer, which I have denoted by the black line, the velocity the red line is the variation in velocity. So it starts with a zero velocity, but then the velocity increases and then it becomes equal to the free stream velocity. So inside the boundary layer, the flow is two-dimensional. So it's a function both of x, the axial direction, and y the vertical direction. Beyond the edge of the boundary layer marked by the black line, the velocity is no longer a function of y. For the very special case of flow over a flat plate, the velocity over here is not going to be a function of x as well. So outside of the boundary layer, for flow over a flat plate, the velocity is strictly going to be a constant. It does not vary with y for any type of surface, but for a flat plate, it's not going to be a function of x as well, and it's called the free stream velocity. The free stream denotes that it's free of the any viscous effects which are apparent near to the surface. This figure is greatly exaggerated to show clearly how the velocity varies inside the boundary layer. In reality, the layer is going to be extremely thin and close to the surface, so the velocity quickly jumps from a value equal to 0 to that of a free stream. So that's what I have written over here, that the velocity is two-dimensional inside the boundary layer. It's viscous in nature. The Navier-Stokes equation is valid inside the boundary layer, and when the actual velocity reaches 99% of the free stream velocity, we call it as the edge of the boundary layer. And outside of this, the velocity is equal to u infinity. The approximations of Navier-Stokes equation which are applicable for flow inside the boundary layer I have already discussed in the course, but this today's specific question is what's going to happen if the if the plate is curved instead of a straight plate. If it is a curved plate, then this free stream velocity is not going to be independent of x. U infinity is going to vary with x, and the variation of the free stream velocity outside the boundary layer with the flow direction x can be evaluated by Bernoulli's equation. Because if you know that the ideally Bernoulli's equation is valid for a frictionless fluid. So Bernoulli's equation can be written for any 2 points in the free stream, and let's say that it's horizontal, so the gravity effects will cancel from both sides. The velocity head on one side and the velocity head on the other side, they are going to be different because it's a curved surface, and hence the flow area available to the fluid is going to be different. So there would be a pressure gradient which can be defined in terms of the Bernoulli's equation, and that's the special case of flow over a curved plate. So for a flow over a curved plate, this u infinity is not a constant, but rather this u infinity is going to be a function of x, and Bernoulli's equation can be used to obtain the variation of u infinity with x. But for the special case of a flat plate, this v approach velocity and u infinity are going to be identical because it has been assumed that the flow is unbound in the y direction. So there is no variation in the flow area available for this case, and thus u infinity doesn't change. But let's assume that it is a case between two parallel plates. So if it's a case between two parallel plates, boundary layer will grow from the lower plate and boundary layer will also grow from the upper plate. Therefore, the amount of area available for the inviscid part of the flow will keep on decreasing as we move in the x direction. As a result of which, the free stream velocity will keep on increasing, and this increase can be obtained using the Bernoulli's equation, and that's what I think your question is. So for a flat plate, no variation in u infinity. For a curved surface or flow between parallel plates, u infinity keeps on increasing as we move in the x direction. So let me just draw this picture once again, such that it would be. I'll stop the share and I'll share the entire screen. So let's say we have a situation in which I have a flow between two parallel plates, developing flow between two parallel plates. And if we have a developing flow between two parallel plates, let's see how it would look like. So I have two parallel plates and the fluid is approaching with a constant velocity. The approach velocity is constant with respect to y. So this is my x and the y, and the v is simply a constant. When we come to when the fluid starts to interact with the solid walls, both at the top and the bottom, and the greatly exaggerated view of the growth of boundary layer will probably look something like this. It will keep on increasing, and then at certain point these two are going to meet, and from this point onwards the velocity profile is known as the fully developed flow. But over here, the flow profile, the velocity profile is going to be, it's going to increase to the free stream value. At that point, it will remain constant, and then it's going to decrease and become equal to 0. So this is the U infinity, and if you see that this U infinity is going to be a function of x. The variation in the pressure between point 1 and point 2, as I mentioned, can be obtained by Bernoulli's equation. In here, the gravity head would not change, but the area available for flow will keep on decreasing. Therefore, U infinity at location 2 is going to be more than U infinity at location 1, and dpdx, that is the variation in pressure, can be obtained using Bernoulli's equation. So I think that's all I have to say about the points raised by you. And if you are not satisfied, or if you have some other things that you would like me to clarify, I will be happy to do so.
So right now there are no follow-up questions. I'll let you know in case there is any.
Okay. And we will wait for 1 or 2 more minutes, and then what I would do is, as we were told, I will touch upon the basics of the subject in the remaining 40 minutes or 45 minutes. And if Manikantala, if you see any question coming up, just tell me that there are questions, and I will try to answer those specific questions before reverting to my discussion about the basic concepts.
Okay, sir.
So I'll start discussing about the fundamentals of momentum, heat, and mass transfer that we encounter in the unified treatment, commonly known as transport phenomena. And in the last part of this discussion, I will show how, through the use of analogy, the different transport processes can be connected together by a common thread. So I will discuss about the commonality after I discuss about the fundamentals of the momentum, heat, and mass transfer.
So there is a follow-up question from Mahadev,
Okay.
who is asking that one same pressure at dpdx equals to 0, does the fluid motion cease, and what is the logic behind that? Also, why the boundary layer separation is early on laminar than the turbulent layer.
Okay. Can you repeat the question once again? There are two questions. The first one was?
The first one is one same pressure at dpdx equals to 0. Why does the fluid motion cease? And what is the logic behind that? Also, why the boundary layer separation is early on the laminar than the turbulent layer?
Okay, all right. First of all, when we talk about the flow over a flat plate, the pressure gradient required for maintaining the flow, since it's unbounded on one side, since the flow is unbounded on one side, that means we have since the flow is unbounded, that means it's in the y direction, it's all the way up to infinity. The amount of pressure gradient requirement for such a flow is so small that it is safe to assume that you do not need any pressure difference, do not need any significant pressure difference in order to maintain the flow, and the flow will continue because of inertia. So the viscous forces essentially acts in a direction to reduce the inertia, to bring the fluid back to rest. But for an unbounded case, this resistance is so small that we can safely assume that the flow will continue for a very long time before viscosity brings it to rest, or the length required for the viscosity to bring the fluid to rest is very large compared to all the dimensions that of the surface that we encounter in our common engineering applications. What was the second part of the question?
So why the boundary layer separation is early
Okay.
on laminar than the turbulent layer?
Right. The next question was about the separation of boundary layers. Now, if we talk about the separation of boundary layers, I guess your question originates more from, I mean, if you look at the book by Fox and McDonald about the momentum transfer, about the fluid mechanics, Fox and McDonald, fluid mechanics by Fox and McDonald, there they have shown that there is a surface and some fluid approaches the surface, and then the boundary layer is going to form from this point. The boundary layer is going to form again. This is greatly exaggerated view of the boundary layer. It will be much thinner in the real situation. So inside the boundary layer, as we move in this direction on a curved surface, the adverse pressure, since the flow area becomes smaller and smaller because of the curved nature of the surface, the adverse pressure acting on the fluid, moving fluid, keeps on increasing. And at some point, the adverse pressure gradient would be such that it would bring the fluid to rest. So let's say at this point, the adverse pressure gradient would be such that it will overcome inertia to such an extent that the fluid velocity is brought to zero. Now, let's think of you being the fluid particle and you are situated over here. Now, you simply cannot stay at that point because there will be more friends, your friends in the fluid particles who are going to come and try to hit you. So you cannot move along the surface. The only way available to you is if you go away from the surface, and thereby creating the phenomena which is known as the boundary layer separation. Now, whenever this boundary layer separation takes place, there's going to be the formation of wicks, and the formation of wicks are essentially low pressure region where the fluid particle, due to the presence of the adverse pressure gradient, cannot move forward, and therefore it has to leave the surface in order to satisfy equation of continuity, because it will be dislodged by fluid particles who are approaching you with a certain velocity. Your second question, related question, is this point. Let's say this point is going to take place at over here at 90 degree. That means, let's say, vertically for the case of laminar flow. But if you see, if you increase the velocity over here and make it turbulent, a turbulent boundary layer, the point of separation is going to come over here on the curved surface. So what makes the fluid particles separate from the wall at a later distance for the case of turbulent flow? That is your question. To answer your question, when the particles are moving in turbulent flow, they carry with them more momentum as compared to laminar flow. So to brought a fluid particle which is moving with a higher velocity and therefore more momentum, you need to have adverse pressure gradients acting on it for a longer time. And therefore, the velocity of the fluid particle in turbulent flow, which was higher to begin with, will become zero at a point later than that of the laminar flow. And this is the reason why the fluid is going to come to rest over here in turbulent flow, and then from this point, it's going to detach from the surface. So the delay in the flow separation due to turbulence present in the system can be explained by the higher momentum being associated with faster moving fluids. This is the practical example of this is if you see a golf ball. Now, as compared to a normal ball, the golf balls, they have dimples over them. The dimples are nothing but points which would create localized turbulence, imparting more momentum to the fluid which is flowing past the golf ball while it is in motion. And since the golf ball has dimples and turbulent flow and less frictional drag acting on it, they will move further as compared to a normal ball of the same size and weight, but without any dimples on it. So that's a practical reason of the delay in the onset of turbulence, but delay in the onset of boundary layer separation by creating turbulence upstream. So if you still have some more questions, I'll be happy to answer. Any
So
other questions so
yes,
far,
he
Manikantala?
has given a follow-up question, but I think you have already answered that.
Okay.
He's telling that it has been taught in the class that if the pressure gradient is less than 0, then accelerating, okay, and if pressure gradient is greater than 0, then decelerating.
Yes.
And if pressure gradient is equal to 0, then the particle at rest in that y. Okay, so he's asking to know that if the pressure gradient is come to 0, why will the particle come to rest? I think so you have answered it already.
Right. And if the pressure gradient is 0, then one of two things may happen. A particle at rest will remain at rest, or a particle in motion will continue to have the constant velocity uh, without any change in velocity. So I have already discussed about that in relation to flow over a flat plate.
There are no more questions as of now.
Okay. So I guess this is what, and Manikantala, please let me know if there are any questions or follow-up questions.
Yes, just now one question has been posted by Sanju Vijayan. He's asking that, can you please briefly explain about transient heat conduction and forced conduction, and what is their basic difference and the governing equations.
Okay. Let me see if I can find the right file to show transient conduction. This is not very well. Just one more minute. When I get the right file, it would be easier for me to explain. Right. Okay. So this is one of the files which I think you should take a look at it. But this is the fundamental file which probably would give you some clear idea. You have asked me to explain what is transient conduction and what was the second thing? What is forced convection? So I'll give you some of the fundamentals, and from the fundamentals, I'll come to the point where I would be able to tell you what is transient conduction and so on. So the first equation that you get in heat transfer is Fourier's law, which you already know, that the heat flow is proportional to the temperature gradient. And second equation, which is so this is phenomenological in order. That means you analyze a large data of what's the heat flow and what's the temperature gradient for a constant surface, and you get this relation where K is the material property known as the thermal conductivity. The Newton's law of cooling is something which is a law of convenience, where the convective heat flow is expressed not in terms of temperature gradient as in Fourier's law, but in terms of temperature difference, where Ts is the temperature of the surface and T infinity is the temperature of the surrounding fluid far from the surface. A is the area, and this H is known as the convective heat transfer coefficient. So the main part of convective heat transfer is to find out relations and or correlations for H. And you are aware of how this, what are the dimensionless group, which is the dimensionless group that is associated with H, that is Nusselt number, where that is defined as HD by K, where H is the convective heat transfer coefficient, D is the length scale. If the flow is through a pipe, that D could be the diameter. If the flow is over a flat plate, that length scale could be the length, the actual length of the actual length over the flat surface, and K is the thermal conductivity of the fluid. Now, I have also derived in the class this specific equation, the energy equation, and let's talk about the energy equation in Cartesian coordinate. So what you get on the left side of the energy equation, if you recollect, this del temperature by del time is the transient term. So whenever there is a transient present in the transients present in the system, the temperature, apart from a function of x, y, and z, can also be a function of time. The rest are the convection, the convective heat transfer terms, where Vx, Vy, and Vz are the local fluid velocities, and these are the temperature gradients in the x, y, and z direction. So the transient effect and the convection on the left-hand side of the energy equation is related to the conductive heat flow, which are characterized by the double derivative of temperature if they follow Fourier's law. So it's K del 2T del x square, K del 2T del y square, and so on. We'll not talk about viscous dissipation much because they are specialized situations which appear only when the temperature gradient is too large or the velocity is too large, which you may encounter for the case of re-entry of a rocket. where the viscous heat generation, the frictional heat generation could be substantial. And Q dot is the generation of heat due to other means. For example, if it's a flow of current through an electric wire, then that's going to generate some amount of current. So this is the entire equation which is there for heat transfer when we consider transient, convection, conduction, viscous dissipation, and generation. And this is the form of the same equation for the case of a cylindrical coordinate systems. And we know what are the different boundary conditions which are used in heat transfer. For example, you could have the temperature could be specified, the equality of temperature or at any interface. So temperature is a continuous function. You can have perfect insulation or an adiabatic surface condition, and this one is very important, the mixed boundary condition, where a conductive heat flow up to the interface must be equal to the convective heat flow away from the surface. So the equality of conduction and convection is another important approximation, another important boundary condition which is used in this. But your question was more about the case of transient conduction, and let's come to that. And the first one that I have discussed is the lumped capacitance method. I am going to talk only briefly about all these because in the main course I have taught them in detail. So the major assumption which makes the case the lumped capacitance method is that temperature is space-wise isothermal. That means for a solid, the temperature is not a function of x, y, z or r, theta, and phi. It's a function only of time at any given instance. So if you have a solid ball which is at 90 degree and you put it in water which is at 30 degree, the temperature of the solid ball will keep on decreasing. The variation of temperature of the ball, if lumped capacitance is valid, it's going to be a function only of time. So temperature could be 90 at one instant, after a few seconds it could be 80 and then 70 and so on. But the entire ball is going to be at 70 at that specific instant of time. And that can happen only when the conduction resistance inside the solid is very small as compared to the convection resistance at in between the solid and the liquid. So the conductivity is so large that the entire solid is going to be at a constant temperature at any given instant of time, or the ball is so small in size that it's going to be at the same temperature at any given instant of time. At the next instance, the temperature may be different, but the temperature inside is going to be the same. So a large thermal conductivity, a very small length, or a very small value of convection coefficient H, and we understand that the resistance is simply 1 by H. So a small value of convective heat transfer coefficient means a large convection resistance. So therefore HL by K, which is dimensionless, which is known as the Biot number, if it is very small as compared to 1, then the resistance, the conduction resistance is small, and therefore we can use the lumped capacitance method which I taught in the course. And the fundamental equation would be rate of heat in minus rate of heat out plus or minus any generation, rate of generation must be equal to the energy stored in a system. So for the still ball which is being quenched in cold water, there would not be any in term. There would be some out because some amount of heat is being lost by convection. It's not generating any energy inside it, but the result, due to its interaction with the liquid, it's losing some amount of energy. So what is out? Out would be minus HA T of the ball at any instant of time minus T infinity, where T infinity is the temperature of the liquid. I think that's what I have written over here. So AS is the surface area, T T is the temperature of the ball at any given instant of time. T infinity is the constant temperature, and rho V, that means M, Cp, C is the heat conductive, C is the specific heat, and D temperature by D time, that would give you the rate of energy stored in the ball. So this becomes the governing equation for transient heat transfer process, which you can integrate to obtain the variation of temperature as a function of time. And the parameters H, the AS, the surface area, rho, the density, V, the volume, and the specific heat together, along with the initial temperature of the ball and the medium, the temperature of the medium. So the variation of temperature with time can be obtained in this fashion, which is known as lumped capacitance method, which is only valid when Biot number is quite small as compared to 1. So this is the relation. If that doesn't happen, if Biot number is not quite small as compared to 1, then there are certain methods which one can try. It could be analytical. We could solve the problem numerically, or there are graphical methods which are also available in order to obtain the temperature as a function of time as well as space. But the simplest possible one is the lumped capacitance model, which gives you the temperature as a function of time only, because it has been assumed that the entire object is going to be space-wise isothermal. Does that satisfy you? If you want any further explanation, I'll be happy to do so.
So there are no more questions as of now.
Okay. So I can quickly go through some of the basics. For momentum transfer, you all have seen the continuity equation, where Vx, Vy, Vz are the components of velocity. So this is nothing but the statement of conservation of mass. So for a constant density fluid, this is the form of the equation of conservation of mass, also known as continuity equation. The other equation that you have seen is known as the equation of motion. And in the Cartesian coordinate, for a Newtonian fluid, this would be the form of the equation. We have worked extensively with this equation, cancelling the terms which were not relevant for a specific problem, finding the governing equation. With the use of the appropriate boundary conditions, we can obtain what's the velocity profile. So this is the transient term. If it's steady state, this would be 0. These three are the convective momentum transport, characterized by the explicit appearance of velocity in each one of them. This is the pressure gradient term. All terms in the Navier-Stokes equation are force per unit volume. So pressure is Newton per meter square, and you have another Z over here. So it's Newton per meter cube. So it's force per unit volume. The terms inside the third bracket are the viscous transport of momentum. They are again, you can easily identify them by the appearance of the viscosity mu with them, and the Newton's law of viscosity gives you this specific form. And here you have the body force, which is rho, g is the acceleration due to gravity, and so on. The relevant boundary conditions are, as we have discussed, no slip at the liquid solid interface. So that, it should be fluid solid interface. So that means the relative velocity between the fluid and the solid at the interface would be 0. And due to the vast variation of viscosity normally between the liquid and the vapor, the shear force getting at the liquid vapor interface would be 0. So these two are the relevant boundary conditions which we have used for the case of momentum transfer. Manikuntala, you let me know if there are any questions.
No, sir, there are no
Okay.
follow-up questions.
Fine. So I have already discussed the heat transfer part of it. So let's talk a little bit about the mass transfer equation. So the fundamental equation for mass transfer is Fick's law, like what we have in the case of heat transfer, which is Fourier's law. So Fick's law essentially gives you the flow rate as if as a function of several things, mostly the velocity gradient. So this is what the Fick's law is all about. The first one is bulk flow. NA and NB are the molar flux of the component A and B, XA being the mole fraction, and DAB del CA is the diffusive flux. So this is molar flux, bulk flow, and diffusion. So if you expand this, this would simply be DAB del CA del X, del CA del Y, and del CA del Z. So that's essentially Fick's law, where we have bulk flow and diffusion both present in a system. And the species balance equation in Cartesian coordinate system, like the same way we have seen in the case of heat transfer, we have a transient term. This is a transient term where the concentration of species A could be a function of time. A convection term, again characterized by the appearance of the component velocities over here. Then we have the conduction or diffusion or molecular transport. They are synonymous, and they are, again, the DAB appears over here. So this is the conduction term, and the generation one, which the generation is essentially or depletion would be due to the reaction which is taking place in between component A and other components, for example B, which is present in the system. So these are the fundamental equations of mass transfer that we have discussed extensively in our course. In the relevant boundary conditions that we have, seen are the major feature of this is the homogeneous reaction term, that is Ra, appears in the governing equation, whereas if it's a catalytic reaction, then the catalytic reaction, the term would appear, heterogeneous reaction would appear as a boundary condition. The possible boundary condition, like the way we have in the case of heat transfer, that instead of temperature, the concentration can be specified at a given point. It could be governed by the solubility or the equilibrium between a species which is in the vapor state as well as in the liquid state. So the concentration could be specified. The second one is the same as the combination of diffusive flux. The second one is the diffusive flux to the surface, catalyst surface, must be equal to the reaction which is taking place on the surface. This is in order to maintain a steady state. So at steady state, whatever be the amount of reactant that reaches the catalyst surface by diffusion must be equal to the consumption by reaction at the surface. So this double prime refers to the heterogeneous reaction. So the equality of diffusion, surface diffusion to the catalyst surface and the rate of reaction could provide you with another boundary condition. The third one could be that the concentration at the interface on both sides of the interface are same. It is similar in concept to the temperature being equal on two sides of the interface. The fourth one could be the surface could be impervious to a specific diffusing component at any given location. So let's say you have a glass of water and a lump of sugar. The base of the glass is going to be a surface which would not allow any sugar molecules to pass through it. So if that's the case, it's an impervious surface. It's similar in concept to the perfectly insulated surface in heat transfer. There dt dx was equal to 0. Here dc dx would be equal to 0. And as before, the conductive flux at the solid liquid interface must be equal to the convective flux on the liquid side of the interface. So the equality of diffusive flux and convective flux. This will form the last boundary condition, which may be used for the case of mass transfer. And conceptually, it's similar to the mixed boundary condition for the case of heat transfer. So this is another concept which we have discussed at length in transport phenomena course. And the and any questions so far, Manikantala?
No, sir. No
Okay,
questions.
all right. So the last one I would like to talk about is the analogy between transport processes. This is a topic which essentially gives you the overall story, the main part of the story of transport phenomena. Because in transport phenomena, when we start this course, it's difficult to see the correlation between three seemingly different processes. What is there? What is the common thread between momentum transfer, between heat transfer, and mass transfer? So towards the end, at the end, we have come to the point where we could see that all these different processes can be explained by governing equations which would look similar when, especially when they are expressed in dimensionless form. And if we probe further, we would see that some dimensionless groups appear automatically in in those equations, and for specific values of those dimensionless numbers, the equations will turn out to be identical. So the solution of one process, let's say temperature, can be simply used as the solution of concentration distribution. And this way, this is a great leap forward for the engineer, because let's say it's possible to do the heat transfer experiment in a specific situation, but not mass transfer experiments. It's not possible to do mass transfer experiment. So by performing heat transfer experiments, he or she would gather enough information that would enable her to obtain the results, the anticipated results, with great accuracy, even for the case of mass transfer. So the concept of similarity between these processes and the relations that come out of that discussion is the thread which binds the transport phenomena with heat, mass, and momentum transfer, and gives a complete package to a chemical engineer. So what we have done is these are the three equations which we have. These are the three sets of equation. 1 and 2 constitute one set: equation of continuity and the equation of motion for flow inside the momentum boundary layer, equation of energy for the inside the thermal boundary layer. We have assumed that there is no viscous dissipation, and we have also assumed that there's no heat generation. And this is the inside the concentration distribution. This is the equation, and right away you could see the similarity between these two. The T is simply replaced by Ca, species concentration, and you get identical equations where alpha, which is K by rho Cp, DAB, and if you look at this equation, this mu, which is mu by rho, the kinematic viscosity. So the kinematic viscosity, thermal diffusivity, and the mass diffusivity, they are going to play a major role. You could see that they are going to play a major role in identifying the similarity between these three equations. So the left-hand side is advection. This is the convective flow of mass, of heat, of momentum, and on this side is the diffusive flow. So you look at you non-dimensionalize all these three equations, and what you get are the similarity parameters. This is Reynolds number, this one is Reynolds times Prandtl number, and this one is Reynolds times Schmidt number. And if you look at the boundary conditions, they are also identical. Okay, the only difference is that in the free stream, this U infinity by V in T star is equal to 1, C star is equal to 1, But U infinity by V, that means U star is not equal to 1 unless we talk about flow over a flat plate. So if we talk about flow over a flat plate, this ratio is also going to be equal to 1. So the boundary conditions are of the same form. The governing equations are of the same form, the boundary conditions are identical, and if we could somehow say that if this is 1 by Reynolds number, if this is 1 by Reynolds times Prandtl number, and if this is 1 by Reynolds times Schmidt number, so if you can say that Prandtl number and Schmidt number both are equal and they are equal to 1. So under that very restrictive condition of Prandtl number equal to Schmidt number is equal to 1, the three equations are identical, all the boundary conditions are identical, and that's what is known as the Reynolds analogy. So any solution of U, any solution of T, any solution of C star, or the derived quantities. What are the derived quantities? The engineering parameters of interests are the friction coefficient for the case of momentum transfer, the heat transfer coefficient for the case of heat transfer, and the convective mass transfer coefficient for this. They are going to be identical. But as I said, the Reynolds analogy is valid when Prandtl number and Schmidt number are equal to 1. But that doesn't happen in practice. Prandtl number and Schmidt number could very well be different from the value unity. So in order to extend that, we use what is known as the modified Reynolds analogy, which is known as the Chiltern-Colburn analogy. So a correction factor to this effect, Prandtl to the power 2 by 3 or Schmidt to the power 2 by 3, they are added to this relation. Cf is the friction coefficient, St is the Stanton number, Stm is the Stanton number based on the mass, and when these correction factors of Prandtl number and Schmidt number are added over a large value of Prandtl number, I would be able to obtain what is this correlation for a wide range of Prandtl and Schmidt number. So these are the different relations which one can obtain for the case of momentum, heat, and mass, and this constitutes the the final chapter of transport phenomena that I have introduced in the class. So this is for the laminar case. This one is for the turbulent case, which is also known as the mixed case, because you do not have turbulent from the very beginning. Initially, you are going to have laminar flow, and once you cross the laminar flow, then you become then the flow becomes turbulent. So the mixed flow is the one which you mostly encounter for laminar flow relation, mixed flow relation, for momentum transfer, for heat transfer, for mass transfer, valid over a large portion of the large value of the Prandtl number in such cases. So this is the last part which I have covered in the class. Is there any question in the chat, Manikantola?
No, sir. No more questions.
Okay. I think I have almost reached towards the end, and if there are any further questions, I'll be happy to answer them.
So there is one last question which I can see, where Mahadev has asked, can you give some brief idea on mass transfer in fluidized bed reactor?
Okay, the mass transfer in fluidized bed reactor is a specialized subject, which specialized topic, which do not fall directly into the transport phenomena course, but I would give you some general pointers about it. First of all, in the fluidized bed, the entire situation is highly turbulent. So if you are going to find out what is the convective mass transfer coefficient, you will have to rely on experimental data, and the experimental data on heat transfer in a fluidized bed is they are more common. So you could extrapolate using analogy the equivalent form of the Sherwood number relationship from the Nusselt number relationship. So if the Nusselt number data is known to you, then using this relation, you would be able to obtain what's the heat transfer, convective heat transfer coefficient for such systems. So many of the studies of fluidized bed heat transfer or fluidized bed mass transfer, people generally use some sort of relations which are empirical in nature. So if they are empirical in nature, at least using the analogy, you could switch in between the heat and the mass transfer, and use that for your calculation. So this much I can tell you for the case of convective mass transfer or convective heat transfer in turbulent flow inside a fluidized bed. Similarly, you should be able to find out what's the value of CF, the friction factor, in this case as well. So they do not directly fall under the purview of transport phenomena, but the analogy concept is still valid there.
Sir, no more questions are there.
So I'll wait for 1 more minute and then we'll call it a day. So Mahadev, if you are satisfied, then I think our effort in today's class is fruitful. So if there are any further questions from your side or from anyone who's present, in the remaining very short time, I'll try to answer.
Actually, time is over, sir.
Time's over. Okay, thank you very much.
Sir,
Thank you.
Mahadev has said thank you for such a detailed course, and thanks for the day. That's all.
Okay. So thank you, everyone. Special thanks to Manikuntala and the other TA history for helping me on this course. And I wish all the students the very best of luck. Thank you very much. I will switch off now.
Yes, sir.